Well, thank you all for coming again, and thank you, Jack and Janosch, for taking back my day for CHUtalk by one. So let's just jump right into it. I'm going to be talking about killing the black hole information paradox. But to really discuss this topic, we have to, one, define what information is, what a black hole is, and what the paradox is. So that's what we're going to do. We're going to start out by talking about the laws. We'll define certain terms such as information, energy, and black hole. We'll then delve into the problem, try to understand that before moving on to some of the current proposed solutions. And then we'll talk about what's going to happen in the future, hopefully, presumably. OK, so let's begin by talking about the laws. So there's three main laws that we really need to know about this problem, and that's this. So first, information must be preserved. Energy cannot be created or destroyed for isolated systems. And the last law that we're going to need is that nothing can escape a black hole. OK. So and I'll go ahead and define what each of these things are, such as information, energy, and a black hole, are as we go on. OK, so the first thing is what is information? So suppose you were in love, and you were in love with this person that you've been with for multiple years, and you exchanged letters, you wrote poems, you created memories, got mementos, the whole shebang. And then they decide to leave you for their best friend Jeff, who you always knew you should be a little bit cautious of. And it's fine, it's OK, it's happened now, and in a fit of rage or passion or catharsis or what have you, you decide to take everything that you had in that relationship and then throw it into the symbolic fire. And so a week passes, and then you get desperate and sad because you're like, oh, I miss what we had. And then you think to yourself, what if there was that one thing that I kept? What if there was that one memento that I decided to keep instead of throwing it into this fire? So if you're a sad physicist and you have a rainy Sunday, you pull out a piece of paper and then you start scribbling away your quantum mechanics. And you ask yourself, is this information retrievable? And sadly, yes, it is retrievable. You can, in fact, continue to fuel your obsession with this person if you were to find all of the heat, the energy that escaped your system. You took account all the chemical interactions that happened, transforming one state to another. If you were to capture it all, even the light that emanated from the fire, if you were to capture it all, you could reconstruct what was on that letter or what was that memento that you wanted. So, I mean, the alternative seems pretty ridiculous, right? It's as if saying, if you didn't have that information and that information was lost forever, then it's inaccessible. It's as if it just left this universe, which seems pretty ridiculous if you think about it. So the information is, in fact, retrievable. And that's the main idea here. The information is retrievable, and if you were made in the universe, then you die in the universe. And that's kind of the end of that story. So that's what information is. It's anything that has a state that you can ascribe some sort of property to. All right, so let's move on to what energy is. So the second law says that energy cannot be created or destroyed for isolated systems, and that makes sense. You can't just continuously add energy. You can't just get a free lunch whenever you choose to. If you take account this system, for instance, this room, you have some sort of kinetic energy, sound energy, you have potential, gravitational, electromagnetic, the whole shebang. You just have all these different energies, and they transition between one state to another. But that's it. Every object in this universe has some energy, which is property number 2. And the first property is that it can be converted from one medium to another, from one type of energy to another. And it's just the ability of a system to influence its surroundings. That's as basic as it gets. But in order to really continue with why I'm talking about what energy is, it's more useful to talk about what matter is, or like what light is. Fundamentally, matter and light can be described as quantum fields. And the reason why we need to go that far deep or go that far small is because in order to talk about the information paradox, we have to be invoking something called pair production. So I'll get into that now. So before I jump into this analogy, just imagine that in this room, there's some sort of temperature difference. It's maybe hotter where I am because I'm more beautiful, or it may be like, hotter where other people are because of reasons. Because of other reasons I can't think of. So, so you can define some sort of temperature difference, some sort of temperature gradient. And the laws of thermodynamics tells us that with any sort of associated temperature, you can get an energy. And we've just discussed that energy can be converted from one form to another. And this sort of same principle would hold not just for a temperature field, but it could hold for any sort of quantum field. And for the specific example, the field that I'd like to talk about is the electron field. So if we were to ignore this annihilation or whatever's happening, right here you see that the electron field expends some of the field's energy in order to create a particle, E. So it converts energy. It converts its own energy into a particle, which is just an energy carrier for all intents and purposes. And then you can say, you can actually talk about this process that's going on here. So there's two ways to look at how a field's energy changes. It can either, one, give its quanta to some object, such as the electron over there, and then let the electron exist. Or two, it can create two particles, each with an energy E, which are opposite to one another. So the field has some energy. It creates two particles, so it decreases in energy for each particle. The particles annihilate, and then they give the energy back into the field that created them. So that's a cycle. Another way to talk about it, which is totally equivalent, is you create two particles from your energy state, and then one particle has positive energy and the other particle has negative energy. So you start out with you start out with energy E. You have a +1, -1, which is going to cancel out to 0. And then when they do cancel, it returns back to 0, back to energy E. So there's no net change in energy. And it's the latter definition, when you have a positive energy and a negative energy solution, that we should focus on for the black hole information paradox. OK, so so this is what the matter-antimatter pair production says for an electron field. And it's the same for any sort of field, for proton/photon, whatever, what have you. And the reason why it's important is because all matter is fundamentally quantum. OK? And a prettier picture, if you're a visual person like me, is if you were to zoom in into the vacuum of space, or like even beside you, there are all these virtual particles that are popping in and out of the vacuum by borrowing energy and then annihilating one another and returning back into the vacuum. So this is what some physicists like to call the quantum foam, but just ignore the terminology for now. OK? Yes. Right. So the second law, the main idea is that antiparticle and particle pairs can be born out of quantum fields. And the universe can do this tax-free, which means that every single time we want to send a rocket into space, we have to convert this ginormous vat of chemical potential energy into heat and then mechanical energy as thrust to get a payload into space. But we do that with the cost of efficiency. Every single time you convert from one thing to another, you lose some material in the process. But the universe can do this fairly tax-free. And nothing is being created or destroyed here, because all the energy that is born from the system will die again in the system. OK? And so the last thing we have to talk about before we move on is what a black hole is. And this is a really nice artist's rendition. It's definitely wrong, but it's kind of nice to look at. So black holes weren't first hypothesized in World War I, actually. They go back all the way to 1783, where there's a sad life of, is Tom here? Hi, Tom. OK, there's a sad life of a geologist who once, there's a sad life of a geologist in Cambridge during 1783. His name was John Mitchell, who hypothesized the existence of dark stars, whose escape velocities are greater than the speed of light. So just by using Newtonian dynamics, you can come up with an object called a dark star, which has an escape velocity that is greater than light. So it will never emanate light, per se, but it could emanate heat. Or at least you could see it emanate heat. And so he proposed this idea to the Royal Society, and they subsequently laughed him out because they were like, "You're a geologist, what are you doing?" And surprisingly, this isn't the worst that it gets for John Mitchell, because later on he would go on to invent a torsion balance test in order to determine what the mass of the Earth is, and he dies before he completes his experiment. The apparatus was built, but he dies before he could test it, and then it was passed on to Cavendish, his best friend, and now it's known as the Cavendish experiment, which is pretty sad. And secondly, Laplace, arguably independently, but we're not entirely sure on the historic details. Laplace also came up with some idea that is very similar to the dark star hypothesis, And after he saw what happened to Mitchell, he wouldn't put it in his book. So I don't know what that says about academia, but sometimes you've got to persist. Okay, so this brings me to the punchline of what black holes are. And I kind of gave it away. They're dead stars which meets a certain criteria. After they go supernova, they have this escape velocity property. But yeah, black holes are just impromptu cemeteries. And then if something falls in, then we know that it's unable to get out. And why is it unable to get out? Well, 3 things. First, we have to talk about its energy, and this will be important much later. And secondly, the time dilation and effect. And then finally, the event horizon, which is probably going to be the most contentious part of this entire talk. But let's just jump into it. So the energy of a black hole is given by this formula. This is one of the 3 formulas that will be in here, and you don't really need to know it. You just need to know that it is a function of the mass of the black hole. And if you were to rearrange these constants in a specific way, you see that it's almost a function of area. It's got 4 pi something cubed, so you can kind of squint at it and see maybe there's an r in there. But the reason why this is going to be important is because of, well, one, we need to make sure that the energy of the black hole will continue to be the energy of the black hole. It's not like as if it's going to be creating energy or destroying energy. And then secondly, we have to talk about time dilation. And I've done my best to try to find a GIF of time dilation, and there are not many good ones out there, but this is the best I've got. So at Gabe's reference point, he throws in a monkey into the black hole. And now everything on the outside of the black hole is fine. We all agree that the monkey is falling into the black hole, and we all agree that as soon as it hits this surface, that for some reason or another, the time dilation effect is so strong because of the gravitational pull of the black hole that we don't see the monkey age anymore. We see its clock stationary, it's fixed. So if you were at the monkey's reference frame and I was him, I would just think that you'd be living infinitely long. But what's actually happening is everybody's agreeing that the monkey is time dilating, which means that as it gets closer and closer to the black hole, it'll redshift and more. And effectively, all the information that the monkey would have sent in the instance before it got to the surface of this black hole is continuously being sent out. It's just going to take millions, perhaps billions of years to actually reach us. But there's no conflict of interest here. We're all agreed, except for the monkey, we're all agreed that the monkey never crosses the edge. Okay, but what's at the edge? What actually really happens at the event horizon? And this is when you have to take all your intuition and just put it in the back seat for a couple of minutes. So everything makes sense in the fact that all the information that the monkey was carrying before it hit the black hole surface is still being carried with it. And whatever information it was sending is just glued onto that surface. And that makes sense. If you were looking down at Earth from the ISS, for instance, you see that everybody's moving a little bit slowly. It looks like ants are moving on the surface, but you see that all the information is there and it just takes a while for you to get there. But when you cross the event horizon, if you are that sad monkey and you cross the event horizon, then something pretty profound happens. So before you cross the event horizon, you have all of these degrees of freedom. You can go in any which way you want. You can go in whatever direction you want. But as soon as you cross the event horizon, and at the event horizon, you see no discernible effect. Nothing changes for you. It's as if you're walking into another room and the door's already open, so you wouldn't have noticed that you walked into another room. There's no change. But there is a discernible change for all the things that the monkey can do. All it can do is head into the center of the black hole. So time for us here is the same as the time for the monkey inside the black hole as it is just evolving upwards in this diagram. But all sorts of curves that you could have had here, as in going away from the black hole, cannot exist inside the black hole. This means, imagine you're a skydiver, right? So if you're a skydiver on Earth, or near Earth, you jump out of your plane, and then you have one way down, which is down. But if you are a sufficiently crazy person, or Felix Baumgartner, you can probably get like a jetpack or something, and then strap it on, and then as soon as you jump out of a plane, you can go upwards. Now, if you were in a black hole, that solution is not allowed. You cannot put on a jetpack or anything to get out of a black hole if you are a massive object or if you're a light. If you are a faster than light particle, then all bets are off. I don't even know how you got in the black hole in the first place. But yeah, so for those two cases, if you're a massive particle or you're a massless particle, then your time has to go forward, and that forward direction is the center. Okay? So that's a pretty important point. So the event horizon separates all the events that were happening inside the black hole from the events that are outside the black hole, because there's no way that anybody inside the black hole can ever convey the information that they took with them to the outside. And that also preserves information in its own way, since everything that's happening in here continues to happen in there. And there's no reason for the information in here to get out here. So information is preserved, but this is a classical black hole. It gets much stranger when we get into the quantum picture. So just to recap quickly, the main ideas. If you're made in the universe, you die in the universe. Particle and antiparticle pairs can be born out of the background, quantum fields, and an event horizon disconnects the events happening inside the black hole from the events that are happening outside. And that's a permanent thing, maybe. Okay, so what is the problem? We're finally getting to the problem. So Hawking in the 1970s showed that using law 2, law 1 implies that there's a contradiction with law 3. And you're probably asking yourself, what does that even mean? So we should probably use our favorite quantum mechanical beating stick, Schrödinger's cat. And so let's just go on a journey with Schrödinger's cat. So we throw the cat. Oh man, we're so mean. We throw the cat into the black hole, and the cat has some sort of superposition for its quantum state, which is basically a fancy way of saying it has some information. So it has some information, which is in this case particularly quantum information, not what you're thinking of, just regular old information that is quantum mechanical in nature. Its wave function is being thrown into the black hole. From our outsider's perspective, we all agree that it just redshifts until it gets to the surface, and then you can just see the image of the cat on the surface, kind of frozen in time, and then keeps going redder and redder and redder. But all of the information that the cat was using in our universe stays in our universe on the black hole's event horizon, because it's time dilated. It's not actually on the event horizon. It's just time dilated to stop before it hits the event horizon. But Hawking came along and said, oh, do you guys remember the pair production part? Yeah, so he said that when you use the pair production of the near the black hole's event horizon, well, you're going to create two particles. From what energy? You use the black hole's energy to create these two particles. So the black hole's energy, either you can look at it in one of two ways. It either goes down to, or you can do a negative and a positive, and then they annihilate. But either way, let's pretend, for instance, the energy of the black hole goes down two particles because you create two of them. One of the particles returns into the black hole and gives the energy back. But the other particle goes out to infinity. It escapes. And by doing so, the black hole loses some of its energy. Now, this isn't a problem just yet. So Hawking showed that the particle and antiparticle pair creation at the event horizon causes the hole to evaporate. Now, how did he show that it was going to evaporate? You just notice that the black hole loses some energy. That doesn't mean that it has to vanish. Well, yes, it does. That's a matter of fact. It does. The energy of the black hole, you can use it to calculate the temperature. And it's a pretty easy formula. You just divide the energy by the Boltzmann constant. It's just some constant. It's fine. But the temperature is related back to the energy through entropy. And if you were to do the integration or whatnot, just divide everything out, you just get here, T is equal to EBH over KB, so you just get a KB factor out in front, but then you have a DE over E. And then you integrate, you get some logarithms. It's all ugly, it doesn't matter. And you just, at the end of the day, you get that the entropy is proportional to the area of the black hole. But if it's proportional to the area, and the area is connected back to the energy, and if the energy shrinks, then the area is going to shrink. So the black hole itself, the entirety of this gigantic gargantuan mass, is going to just shrink just a little bit. But remember, the universe can do this process tax-free at how much ever times you want it to. So you see, as a person that's standing outside, after upon millions of years, that the black hole is slowly starting to shrink, using up all of its energy, and then radiating out all of these particles using pair production. So continues to shrink, until one day it's just poof, gone. And now, you're going to ask yourself, what happened to my cat? So Schrodinger's cat falls into the black hole. We see the cat freeze at the event horizon. The black hole evaporates, and there is no more event horizon. It's gone now. And you have to ask yourself, what happened to the cat? Where is the cat's information? And this brings upon us one of two solutions. We either say that information is lost forever, or we say that objects can escape from the black hole. Now, if information is lost, that's basically, for the people that are doing physics in here, that's like saying that you don't have unitarity in quantum mechanics. And you're screwed if you don't have unitarity in quantum mechanics. You can't do quantum mechanics. So we really like to preserve information. And having things escape out of a black hole, while that is pretty obscene, it's not the worst of the possible solutions out there. So Hawking, when he posed this problem, people chose this route, the violation of objects escaping from the black hole, as the route to go on. So what is the solution? I've hyped up all this problem, but I should probably get to the punchline. And the solution here is we don't really know. There's two solutions, kind of. They kind of work. The first one is Suskind's solution. Leonard Susskind took the idea of 't Hooft, and I can never say his name right, but I'm pretty sure it's 't Hooft. And he used this principle called holography, or complementarity, which is basically like saying, if for this TV, for instance, or a cathode ray tube TV, what's actually happening is that, on the inside here, there's an image being projected onto this two-dimensional screen. Now, they argued that this is just a dimensionality issue, that when the particle falls in, you can treat it as like a two-dimensional particle, and then it's projecting its information and leaving it on the event horizon. Now, this is different to what people were saying when you stood outside the black hole and then you tossed a cat in. When you toss the cat in, it just time dilated, but it never got to the event horizon. You just see that it's plastered on the surface without ever reaching the surface. But this is actually saying that the particle's information is encoded in the event horizon itself. So now the event horizon becomes this physical place where you can put stuff in, or on, or in, technically. But how does this resolve the paradox? Well, as the black hole shrinks, the way that it shrinks is that it reverberates just a little bit as it goes down. And so this fluctuation, this perturbations of the event horizon releases this quantum information that's trapped on the surface of the black hole. And if that doesn't sound like BS to you, I don't know what does. But the unintended consequence of this hypothesis is pretty profound. So for those of you that know what entangled particles are, this would make more sense. But when you have a particle-antiparticle pair that come out of nothing, let's say that one has totally the opposite properties of the other. Now, if they had spin properties and they're entangled in terms of spin, if one of them falls in, if you determine what the spin is of the guy that escaped to infinity, then you automatically know what the spin is of the particle that's on the inside of the black hole. Now, the reason why that's a problem is because way back in the day, Einstein used entanglement to show how ridiculous quantum mechanics was, but it backfired on him. He said that you can only have two particles entangled at one point in time. So now if this particle that fell into the black hole projects its quantum information to the surface of the black hole, then the particle that's out at infinity has its entanglement with the black hole's surface and the particle that's on the inside. And you can't have two things entangled at once. So this led Susskind to say, well, maybe the entanglement isn't projected onto the surface, but they have quantum wormholes that connect them. OK, it's fine. I don't believe it. And then the second one is Almiri, Marolf, Polchinski, and Sully said that there's a firewall, which means that if you get close to or cross the event horizon or at the event horizon itself, every single thing that crosses the event horizon is terminated, that it is entirely destroyed, all the information is lost, and because of the weird properties of the event horizon, you can actually have information loss. But it somehow also preserves the information of the thing that it eats, and again, half the people that are doing black holes absolutely hate it because it violates another principle that Einstein came up with, which is that a free-falling observer would never know the difference of going into a black hole. Like, you would never be able to tell the difference of when an event would happen. So in this one, you would have to give up the Einstein equivalence principle, and for this one, you would have to give up what entanglement, the monogamy of entanglement, it's called. Which I don't know about that. Seems pretty classical-minded to me. Okay, so that's the current solution that Susskind and 't Hooft proposed. So Stephen Hawking made a bet in 1993, shortly after I think I was born, and he said something along the lines of, I think information is not preserved. I think it's totally lost. And so he bet with Kip Thorne against John Preskill of Caltech. And in 2003, he walked back that bet. He said that he conceded because he came out with a paper that basically showed a different kind of version of Susskind's complementarity. So the idea of holography stuck with him enough that he would say later on that he concedes the bet. But I think it was in 2011, he said pretty cheekily, he said, I wish I gave Preskill a burnt encyclopedia of baseball instead of what I gave him, because he could just retrace the information and reconstruct it, that's the most pettiest thing I've ever heard, but it's great. But later on, Hawking came up with his own solution. This time it wasn't the same solution as Suskind's, which is also pretty dubious. This came out in 2015, and there's a lot of work that needs to be done here. But he basically said, Hawking radiation that's happening at the event horizon, well, whatever thing is falling into the event horizon, it'll just copy that information because it was born as a clean slate. It'll just keep a copy of whatever fell in, and then it'll propagate out to infinity. Now, this doesn't solve the entanglement issue. This also posits that the information that's being born has a clean slate, which is extremely strange. I don't know what I said either, to be honest. Yeah, but like, trying to do this, by the way, was extremely confusing because nobody could agree on what they were saying. So I wasn't sure what he said. Yeah, so this solution also has a lot of work to be done, but yeah, so outgoing Hawking radiation will have a chance to adopt the infalling matter information, which, okay, fine. As you can tell, I'm probably not really convinced by either of these arguments, so we can finally move on to what I'll be doing here at Cambridge and possibly what is in the future of this field. So there's a new hope, which I really don't want to drum up, but I think it's pretty cool. And it has a ridiculously long but epic name. It's called Supertranslations and Superrotations. Now, this is the part where I'm going to try to get a little bit more mathy without saying any math. So feel free to call me out in the questions. I welcome it. So the way that you do this entropy calculation is you have to cheat. When you have some sort of geometry that describes the black hole, to do any sort of calculation on that geometry is pretty complicated. So instead of doing it on the geometry, you just pretend you go out to infinity, you say it's flat, and you pretend that you have a universe that just has a black hole and nothing else. You do the entropy calculation from afar because you see that the black hole is just an enclosed box, and you can just say, okay, fine, we can just see what all the entropy is in this box. And then you take that, you walk that entropy back to the surface of the black hole, and then you assert that that is the entropy that you found. That you found through your calculations. Now this has a couple of leeways. So if you put another geometry on that is also flat at infinity, you can also get a different entropy. But most of the time, more or less, it's always the area over 4, or some multiple of the area over 4. Now, what supertranslations and superrotations are is it's a new kind of geometry that do a little bit better, in my opinion, at least for what they're trying to achieve. So now you have at asymptotic infinity flatness, which you can roll back basically using a Lie algebra or using math to connect it back to the surface geometry of the black hole. But you now describe the black hole surface geometry in a different way, in a way that hasn't been done before with other geometries. And I mean, more or less, like, these statements are basically vacuous. But you may get a different entropy, an entropy that isn't A over 4, something that doesn't scale as nicely as area. But even if it does, the thing that you're looking for is you want to find an entropy that scales maybe as area plus the quantum states that are encompassed inside the black hole. By doing this, you don't have to invoke firewalls. You don't have to invoke or try to defeat entanglement entropy. You don't have to figure out holography or whatever. You can say that the entropy accounts for the quantum states. And right now, we have the first term, and the second term is just gone. So if using the method of supertranslations and superrotations, if we can redo the calculation, we might be able to find a way that the quantum states are being preserved all along. And by doing this, we've preserved all three laws. Things that fall in can fall in, and when the entropy is radiating outwards, it carries the quantum information outwards just by the very virtue of Hawking radiation. We don't have to invoke any new thing. We just say that the Hawking radiation takes into account the information that fell into a black hole. And so that's currently what is being proposed by Hawking himself and Malcolm Perry and Andrew Strominger at Harvard. And they've been currently working on this for last couple of years. Whoa. And yeah, it's a pretty interesting time to be alive, I think. So I think that basically concludes my talk. I didn't have much more to add to that, except for this is the only test bed that we really have, at least theoretically, where we can pursue arguments of quantum field theory and general relativity. I mean, this is one of the few places where, other than cosmology, this is one of the few places where we can really test our theories. And so fixing the black hole information paradox is maybe a step forward into really having a productive discussion of merging these two disparate yet argumentative fields. So yeah, that's what I'd like to end on.